So let's look for a moment at the eye, the anatomy of the eye. Here is the anatomy of the eye, as well as the range of the transmission of the cornea. So here you see the transmission of the cornea, and you see that there's a window between 400 nanometers and 1.4 micron. The visible range is just this small part of it. Everything that lies from 700 to 1.4, as I said before, creates a particular hazard, because you do not see that range, but it still gets focused on the retina. So here's the eye, the lens, which is covered by a membrane called the cornea. Between the lens and the cornea is a fluid called the aqueous humor, and between the lens and the retina, sort of filling the eyeball, is the vitreous humor, which is also a fluid. The retina covers about 2/3 of the inside of the eyeball, but this little piece here in the back is what really gives you most of your vision. It's the only part that can actually finally resolve things. There's a very high density of nerves, and this is a blind spot, because this is the spot where the optic nerve comes inside the eye. You may have seen these things printed in books where you have a dot and a cross, and if you cover one eye and you're exactly at the right spot, you can get the cross to be right in the fovea, so you see it, but the dot is imaged right onto the optic nerve, which is a blind spot, and it suddenly disappears as you move to the right distance. As I said before, any light in the ocular focus region travels to the retina. That's anything within that range here. Travels through the cornea, and is focused by the lens onto the retina, and if you're unlucky, right onto the fovea. Cause retinal lesion. In case of very high exposure, like the one we just heard about in that report, it will create bleeding and even gas formation. Even if the exposure is not too severe, you can get a disruption of the retina, or even a detachment of the retina. And in case of very intense pulses, and high energy intense pulses, not low energy, but high energy intense pulses, you can get so much evaporation or such a shock that you actually change the physical structure of the eye. The near ultraviolet region, sort of immediately below the edge, the cutoff, the transmission cutoff of the cornea, the light gets absorbed in the lens, actually, and it can actually create some opacity here, because it changes the proteins that are in there, and you affect. This is something that could, in principle, be repaired, because you can take the lens out and you can put it's like a cataract operation. You can put in a plastic lens. If you go further out to the UV, the light doesn't penetrate in the eye. It really gets absorbed on the outer layer of the cornea, and it actually damages the outer surface of it, creating, retinas, tears, and permanent damage to the cornea because, again, of photochemical denaturization of the proteins. Incidentally, and ironically in a sense, some of these techniques are actually used for laser surgery. The infrared is much the same, gets absorbed on the and with infrared I mean not what we normally call infrared, to the red of the visible spectrum, no, to the red of the ocular focus region. So infrared radiation, like CO2 radiation, for instance, again causes corneal lesion and a cataract-like effect on the cornea, which can be just as serious as damaging the retina. Case history number 2. This was somebody who had actually read in Laser Focus about that other accident that was the first accident that I read to you. As I read my November issue of Laser Focus, I took note of the eye injury report, curious about the particulars of this novel accident. At that time, in the late 70s, early 80s, laser accidents were still somewhat of a novelty, although that is rapidly changing with, a couple of, dozens of eye injuries a year in laser labs in the US alone. Even though I have been working with lasers for 5 years in the presence of many of the same hazards pointed to in the article, I didn't think while reading it, this could happen to me, but it did. On January 22, 1982, I spent several hours aligning a low-power frequency doubled neodymium YAG beam through a dye laser setup. In order to see the 532 nanometer pump beam propagation, I was not wearing goggles. Another common mistake, right? The goggles protect your eyes, but they also prevent you from seeing the beam you need to work with, directly at least. I had also removed a beam block intended to absorb a Brewster's angle reflection to observe end pumping of an amplifier cell. The green power was increased to determine the extent of dye lasing without replacing the beam block. I did not put on goggles. While placing a power meter at the dye laser output, I leaned over the uncovered amplifier and caught a reflection in my right eye. While I do remember seeing a green flash, there was no pain. I was not immediately aware of any significant eye damage. It wasn't until I shut the lasers off and returned to my desk to record the day's activity that I realized I had a blind spot comparable to a camera flash, but only in my right eye. It was almost 5 p.m. on a Friday, and I didn't report the incident because I couldn't believe that any serious damage was done. By Saturday afternoon, I knew I had a problem. Monday the 25th, I notified our safety division and started my visits to an ophthalmologist. The initial examination supported the probability of permanent damage, although bleeding in the affected area obstructed detail. By the end of the first week, peripheral vision around the spot was improving. I was encouraged and felt fortunate considering the negative potential of this careless mistake. But by week 2, peripheral vision had declined. Distortion of resolution around the spot became more noticeable due to additional blood pooling under the retina. If this bleeding were to persist, laser cauterization would be necessary. So here's an example of, not even a very significant exposure that led to significant problems. Okay, one parameter that is often used to give an indication of what the eye can take is shown in this diagram here, which shows on the vertical scale absorbed retinal irradiance in watt per square centimeter. And remember, watt per square centimeter is what is used for CW lasers, not pulsed lasers. Versus typical retinal image size. Different objects create different images on the retina. The sun, for example, is right there. It creates an image of about 100 micron diameter on the eye, and creates an irradiance on the order of 1 watt, a little above 1 watt per square centimeter. You can see two thresholds on that on this graph. This is the retinal burn threshold for a 10-second exposure. For a 10-second exposure, this causes image size versus irradiance. This causes an actual burn spot. So the OSHA has set this line here as the maximum permissible exposure for a duration of 0.15 seconds, basically the blink of an eye, the time it takes to, you know, move your eye away if you were to ever have that, which is about a factor of 3 lower than this retinal burn threshold for a 10-second exposure. Notice this star here. This is a 1 milliwatt laser, a 1 milliwatt laser, which is right on that maximum permissible exposure. It's still, you know, somewhat below the burn threshold for 10 seconds, but it is right at the maximum permissible exposure. If you take these little handheld diode lasers that you can buy in the store now, they are 1 milliwatt or sometimes even 2 milliwatt. So they exceed. If there's somebody sitting in the audience and, you know, accidentally going by your eye, shining into your eye, that is right at the threshold, the maximum permissible threshold. I'm going to show you some figures here, and then we're going to look at a couple of case studies. And I have to warn you, I don't want you to take notes, because in order to calculate what you need for your situation, you will have to go to one of the websites that I will write on the board at the end of this talk and sit down and actually calculate the specifics of your lab, your laser, your lasers if you have more than one wavelengths, because there are no general rules, because there are so many different parameters, namely pulse duration, wavelengths, pulse versus CW, and so on. Okay, so here are some maximum permissible exposures for lasers. A CW laser, depending on whether it's UV, ocular focus, or infrared, ranges from a tenth to 5 thousandths of a watt per square centimeter. And pulsed lasers range from 10 to the minus 4 to 4 times 10 to the minus 3 joule per square centimeter. So let's take an example. This is a laser that's no longer used very much, but you know, some labs still have them. Imagine dealing with a reflection from a ruby laser pulse. So ruby laser is at 694, that's at the edge of the visible region. You can still see the radiation, but the eye is not very sensitive to it. A worse example would be titanium sapphire, which is at 800. You still see a deep red, but you really only see a fraction of the intensity, because you know it's right at the point where the sensitivity of the eye falls off. So even though you know you think you see the red spot, it's much weaker than it actually is. Okay, so let's say that we have 300 millijoule per pulse at 694 nanometers in a 20 nanosecond long pulse. The typical beam size of a ruby laser pulse is on the order of 6 millimeters. It's pulsed, right? We have a 20 nanosecond pulse, so we have to deal with energy density. Well, the energy density here is about 1 joule per centimeter square. If you take the 300 millijoule over 6 millimeter diameter beam. So imagine, and this is standard practice in a pulsed lab, you take some sort of shiny paper that you put into it to examine the mode structure. So what you do is you put the card in the beam and you let a pulse hit the card, and then you look at the burn spot to determine the mode of the laser. That's standard practice. But these little cards are slightly reflective. So say 2% reflection, so that's 2 times 10 to the minus 2 joule per centimeter square. And if you look at the maximum permissible exposure, this is ocular focus. It's pulse, so 10 to the minus 4 joule per square centimeter is the threshold. So if you were to put that card in the beam and send a reflection to somebody else standing on the other side of the table or even the other side of the room, you would exceed this maximum permissible exposure by more than a factor 100. So potentially creating permanent eye damage. Two more examples. A neodymium YAG laser, 1064, so it's 1 micron, invisible, but it is within the transmission window of the cornea, so or the eye. Actually, it strikes the retina. Imagine a 30 millijoule, very low energy. I mean, you can easily get joules out of YAG lasers. In fact, the cheapest YAG laser that you can buy probably nowadays generates a joule of radiation. Okay, but this is not a standard YAG laser. This is one that creates picosecond rather than nanosecond pulses. So let's say 30 picosecond pulse, beam size 3 millimeter. It's pulse, so it's energy density that matters. Suppose somebody puts a glass slide into the beam just to split off part of it. Standard practice again, except that you should never insert an optical element in an optical beam without first blocking the beam. But let's look at what a 4% reflection from a glass slide would do. We have to deal with energy density. So if you look at the energy density, if you put these numbers in, you get 0.3 of a joule per square centimeter. If you take a 4% invisible reflection from a glass slide, that's 1 times 10 to the minus 2 joule per square centimeter. The maximum permissible exposure for this laser is the same as that as the ruby laser, because it's within the ocular focus range and it's pulsed. The difference is that one is visible, the other is invisible. And we see that we're again about a factor of 100 above the maximum permissible exposure. Let's take another scenario here, very different. A CW argon laser. They emit around 500 nanometer, depending on the line on which you operate them. They're definitely ocular focus, most lines, and visible. Let's say it's a 5-watt argon, not a very high power, but one that you might typically have in your lab. Beam size 2 millimeter. So it's a continuous laser, so we need to look not at energy density but power density. Well, 5 watts, 2 millimeters square gives you a power density of about 100 watt per square centimeter. And if you look at the table, the maximum permissible exposure is just 5 times 10 to the minus 3. Of course, that's if you look straight into the beam, which is very unlikely. Or perhaps, as one of the accidents I'm going to tell you about, it's not that unlikely. But let's assume that nobody here will actually get it in their brains to look straight into the beam. Let's imagine that you just block this beam with a beam block that diffuses the light around. And if you take a 90% reflection from a diffuse surface, like a piece of cardboard, let's say, and of course the intensity depends very strongly on R. It falls off as 1 over R squared, but you reach the maximum permissible exposure for 1 second exposure at 70 centimeters, 2 feet. So if you're closer than 2 feet from that piece of cardboard that scatters the light, the intensity of that spot you would probably not look at it, but if it's in your peripheral vision, it actually comes frighteningly close to the burn threshold of your retina.